Try to speak louder.
Sorry. Okay, so my name is Rita Neves, as Mercedes said. I'm going to present a work I've been doing in collaboration with my supervisors, Mercedes Martin Benito and Javier Olmedo, on states of low energy in cosmological spacetimes. And in particular, we're going to use these states as the vacuum states of cosmological perturbations in the context of fluid quantum cosmology. So states of low energy have been introduced by Obermann in this work in 2007, which is actually based on an earlier result by Fuster, who showed that the renormalized energy density, when smeared along a time-like curve, is bounded from below as a function of the state. So in other words, there is a state that minimizes this quantity. So Obermann particularized this result for generic FLRW models for cosmology and defined a procedure to find this state that minimizes this quantity by minimizing it mode by mode. And these states seem to be good candidates for vacuum of cosmological perturbations because they minimize the regularized energy density, and also because, as Obermann showed in his work, they are exact Hadamard states. And this is a proof that other proposals don't enjoy of usually, the explicit proof that they are Hadamard. So let us consider we have a field with whose Fourier modes have obey this equation of motion, which will be the equation of motion for the Fourier modes of cosmological scalar and tensor perturbations. Here dot is derivative with respect to time, and h is the Hubble parameter, so a dot over a, where a is a scale factor. And the omega function here is going to depend on our theory and our model. So we're going to leave it generic for now. And the idea of states of low energy is that they minimize the mode contribution to the smeared energy density. So that would be this quantity E. In parentheses here inside the integral, we will have the energy density of the mode at a given time period. And what we do is smear it with this smearing function f. And f is smooth and positive and compactly supported, so we can define directly f squared, which we will further on. We smear this quantity, the energy density, along a given time window given by f. And the total smeared energy density would then be an integral over all the states of this quantity. And the strategy that Obermann proposes is that to minimize that quantity, since that is a quantity that is more difficult to manipulate, we minimize its integrand. So we minimize this one, the mode contribution. And this will lead us to the state of low energy that is associated with the smearing function, because in general, the resulting state of low energy will depend on our choice for this smearing function. So this deserves some thought, because we are introducing an ambiguity here, which is the choice of smearing function. And to understand that, it is useful to think about what happens in maximally symmetric spacetimes. In Minkowski, the situation is trivial. The states of low energy are trivially identical to the Minkowski vacuum. And actually, the state of low energy does not depend on the choice of smearing function at all. And it's actually a state of minimal energy because of that. But Obermann shows that this only happens in ultrastatic spacetimes. In de Sitter, however, where we also have, where the notion of preferred vacuum is the Bunch-Davies vacuum, we find that the state of low energy selects the Bunch-Davies vacuum as long as the support of the test function is on the distant past, sufficiently far in the past. So this hints at that that the choice of test function can have an important role. Other interesting properties of states of low energy are that their ultraviolet behavior is independent of F. This is not particularly surprising, because in ultraviolet, short scales should be Minkowski. However, in the infrared, their behavior also only depends on F up to a constant. So it is, they always have the same kind of behavior for any test function. Furthermore, as also shown in this work, when we use states of low energy as the vacuum of cosmological perturbations, there is a qualitative agreement with observations, by which they mean that the power spectrum of primordial perturbations at the end of inflation, which is called the primordial power spectrum, has the correct qualitative behavior so that it can agree with observations. as long as the model has a period of kinetic dominance prior to inflation. And this is precisely the case in loop quantum cosmology, which made these states even more appealing to use in this context.
Rita, sorry, some people cannot hear you very well. Can you try to speak closer to the microphone or a bit louder, please?
I don't know when my microphone is. Let me put.
Okay.
Let me put an extra microphone here. Can you hear me now?
I hear you as before.
Oh, damn it.
I think, but
okay.
Yeah, maybe a bit better.
I'll try. Okay, because I don't know if it's picking up this microphone. All right. So, sorry about that. I can't go back a little. Okay, so yes, all those properties made these states very interesting as to use as vacuum states, cosmological perturbations. And let me go into a little bit more detail about cosmological perturbations. We study cosmological perturbations because we want to find a connection between predictions of our theory of the very early universe and observations of the CMB. And the idea is that in the early universe, we have a period of accelerated expansion, which is inflation, which I'm representing here in red by its inverse of the Hubble radius. And in standard cosmology, we fix the vacuum of perturbations usually at the onset of inflation, because shortly before we have the singularity. At the onset of inflation, there is a natural vacuum, which is the Bunch-Davies vacuum, because inflation is quasi de Sitter. And then once we fix the vacuum, we have initial conditions for the equations of motion, when we can evolve them, the perturbations, and we find that they oscillate as long as they're inside the horizon. When they cross out of the horizon, they freeze out, and they remain frozen for as long as they are outside the horizon. And they will only re-enter until very late after inflation ends, and we enter a period of decelerated expansion. And this line starts to come down because we have decelerated expansion. So that is why what we see in the CMB, which is very late after inflation, is generated in the very early universe. But this is standard cosmology, and in loop quantum cosmology, the picture is different. So loop quantum cosmology, for anyone who's not familiar, is a non-perturbative and background-independent approach to the quantization of cosmology, and it applies the techniques of loop quantum gravity to cosmological models. And its most outstanding result is that of the singularity resolution. So in FLRW, minimal coupled to a scalar field, which we use as internal time, we find that the singularity is resolved in terms of a quantum bounce. So the volume has a minimum non-zero, a minimum which is positive, which connects a contracting epoch of the universe with an expanding one. And away from the bounce, the dynamics agrees with the classical dynamics of either a contracting or an expanding universe, and of course, close to the bounce, it doesn't. And the volume never goes to zero, so the energy density doesn't diverge, and so the singularity is resolved. But the bounce is kinetically dominated, and inflation is potentially dominated. So before inflation, we have a period of kinetic dominance. Right after the bounce, we have a short period of superinflation, and then a period of decelerated expansion, all before the slow roll inflation begins. So now you can see that to start, it no longer makes sense to fix the vacuum of cosmological perturbations at the onset of inflation. And it no longer seems natural to do it at that point because we have pre-inflationary dynamics. And if we fix them before, we usually fix them at the bounce, but we can also fix them in the contracting branch. Then you see how some modes might feel these differences in the background. They might reach the onset of inflation in an excited state with respect to the Bunch-Davies vacuum of standard cosmology. And then they might freeze out at a different value, and that might affect the primordial power spectrum. So this is what we want to explore by fixing the vacuum to be the states of low energy. So the recipe is to fix the vacuum, evolve with the equations of motion, which will now have corrections from loop quantum cosmology, and compute power spectra at the end of inflation. So let us see what happens when we use states of low energy in loop quantum cosmology. First, we fix our model, by which I mean that we choose a particular approach to loop quantum cosmology, which is hybrid loop quantum cosmology, which just relates to how we incorporate cosmological perturbations. Essentially, it gives us a particular form for our omega in our equation of motion. We also have to fix the potential of the scalar field and some parameters that are free. And then we need to fix our vacuum. And for that, for choosing states of low energy, that means choosing the smearing function, which, let me remind you, chooses what our time window is, where we are going to minimize the energy density. And here we find two main strategies within loop quantum cosmology. The first one is to let the states of low energy know about the whole evolution, in quotation marks, because the smearing function has to be compactly supported. And for this, we use a smooth step function. We use a smooth step because we have seen that the results don't depend on the form, the shape of the smearing function, so we only care about its support. And we use a smooth step function that includes the bounce, that is centered around the bounce, and is sufficiently wide. If it is sufficiently wide, then the results also don't depend on how wide exactly it is. On the other hand, one might also say that in loop quantum cosmology is a simplified scenario with respect to loop quantum gravity, and this might be the reason why we have a nice symmetric bounce. We might want to remain agnostic about pre-bounce dynamics, and we can maybe not want the state of low energy to know about those dynamics. And in that case, we would shift our step function to only see from the bounce onwards. So essentially, our starting point of the step function will be at the bounce, and we will want the steepness controlled by this parameter delta to be very high. So delta would be very small, so that it sees the bounce and goes on to the future. So these are the two main choices for the test function that we consider natural within loop quantum cosmology. And when we compute the primordial power spectra for scalar and tensor modes, so power spectra at the end of inflation, we see that the results don't care about these two choices. They're insensitive to this choice. So for both, we have essentially the same power spectrum. So we can see that there are some numerical differences, but this is essentially the same power spectrum. So this is interesting because whereas in the beginning we had an ambiguity that we were introducing in the choice of test function, we see that in loop quantum cosmology there are two natural choices for them, and the results don't distinguish between these two. So we no longer have that ambiguity there. Now, we may also wonder what happens when the state of low energy doesn't know about the bounce. So instead of beginning the step function right at the bounce, we can see what happens when we move its starting point a little bit away from the bounce so that it doesn't include it. And the idea behind this is that this way we can maybe disentangle in our results in the power spectra which effects are coming from the bounce and which effects are coming just from having a period of kinetic dominance prior to inflation. Which can be achieved, a period of kinetic dominance prior to inflation can be achieved in a classical scenario as well. It doesn't have to come from loop quantum cosmology. And in this case, we do see that the power spectra is sensitive to this choice. So in gray here, I'm showing what I was showing before. So our power spectrum with oscillations and power enhancement. And we see that as we move away from the bounce, these oscillations die out and the power enhancement does as well. Then we end up with this non-oscillatory power spectrum. And so we can say that in this scenario, then the oscillations and the power enhancement are coming from the bounce alone and not because we have a period of kinetic dominance prior to inflation, which is interesting. So to summarize, I hope you were able to hear anything. we saw that states of low energy are essentially they're good candidates, at least, for vacuum of cosmological perturbations in general, because they are Hadamard states, they minimize the smeared energy density, and they offer the possibility of agreement with observations as long as there is a period of kinetic dominance prior to inflation. Within the context of loop quantum cosmology, we saw that we have two choices for this test function, which a priori is an ambiguity. We have two natural choices for it, and the results don't depend much on this choice. So they're insensitive to the choice of test function. If on the other hand we don't include the bounds, then we can effectively compare loop quantum cosmology with a possibly classical model with kinetic dominance before inflation, and we see that the effects from the bounds are visible in the power spectrum. Now, since the power spectra is not what we directly observe in the CMB, obviously, the primordial power spectrum, what we are doing now is to look to perform a Bayesian analysis so that we can constrain some parameters, either of the states of low energy, of the vacuum, I mean, or parameters of the quantization itself as well. So that's it. Thank you for your attention. I don't know if you could hear anything. I'm sorry.
Thank you, Rita. I could hear you well. And I think... All right, so time for questions. I see a hand raised by Gerardo.
Hi, Rita. Thank you for the talk. Could you comment on how do these vacua depend if you change the shape of the function, not only the support?
Yes, they don't depend at all as long as the support is wide enough. So if, as long as, when I say wide enough, I mean it sees the bounce and it sees the kinetically dominated period. And in that case, unless you do something very drastic, like completely suppressing like the bounce, for example, it doesn't depend at all on the shape of this test function. I don't know if that answered your question. If it is very short, if the support is very short, then it does depend on the shape.
Okay, I see. Thank you.
The vacuum, however, the power spectrum at the end of inflation kind of washes some effects out. So the effects on the power spectrum tends to be less enhanced.
Álvaro?
Hi, Rita. There's any physical interpretation of this smearing function?
The physical interpretation?
Yeah.
The smearing function is how we define what is the region in time where we are minimizing the energy density. So we care about minimizing the energy density in this certain region. That's what we're doing with the smearing function. And since we're not even caring a lot about the shape of the smearing function, then it's just really just defining the window.
Okay, thank you.
Valentin?
Yes, thank you, Rita, for the talk. I have a very naive question, which is, how does this whole system, the evolving universe and the quantum state on top of it, evolve if you evolve it backward in time to before the bounce? What can you say about that?
So the bouncing loop quantum cosmology is symmetric. So you have a symmetric universe. I actually don't remember. I think you just have the symmetric universe. It's just it is contracting a universe instead of expanding. I don't know in the big picture if you also have a kinetically dominated period and then a potential dominated period as you do in the expanding branch, but I would say so. You have the kinetically dominated period for sure because the bounce is kinetically dominated, but not sure about the potential dominated period.
Okay, Ivan?
Thank you, Rita, for the very clear talk as usual. My question is just technical. You said that as long as the support of the test function in time is sufficiently large, the power spectrum remains the same. What do you mean by sufficiently large? How large is sufficient?
Like, 60 or 100 Planck seconds. So
The order of 100. Thank you.
we went all the way into the end of the kinetically dominated period, and if you finish there, or if you finish well into inflation, it no longer matters as long as you catch the bounce and most of the kinetically dominated period. The bounce is the one that affects it the most.
Thank you.